everything that imparts a huge amount of energy into its surrounding. So example of these processes are supernova events, novae, gamma ray bursts. All of these are transient events. All of these happen in a matter of either weeks or months up to a year. And all of these have this tremendous input of energy into the surroundings. One of the process that I'll be talking in detail in this talk is what we call as the process of accretion. So in this case, the process of accretion, specifically in X-ray binaries. So X-ray binaries are a system where you have a compact object like a white dwarf, a neutron star, or a black hole in a binary orbit with a main sequence or a supergiant star. So what happens is this compact object starts accreting matter from the main sequence star, and more often it forms an accretion disk around it. Because of the energetics that is involved in this process, because this is matter falling under huge gravitational potential of a compact object, the most of the energy emission happens in X-rays. But you see a host of other emission processes which radiate in multi-wavelength. So for example, the optical emission from either the accretion disk itself, or what we call reprocessing, happens in optical. You have the companion star, which more often can be detected in with optical telescopes. And then these systems also have jets present in them. So these jets are these relativistic outflows, which more often are prominent in radio. So these systems form a very efficient multi-wavelength emitter. So just a brief history of how these are formed, these compact objects are formed. So for a star which is roughly less than 9 solar mass, it undergoes, like, for example, like Sun, it undergoes a red giant phase, and then it undergoes a planetary nebula phase where it rapidly loses out its outermost envelope, losing almost up to 95% of its mass. And then at the very core, there's a white dwarf which is formed. So after the planetary phase gets over, you see at the extreme core, this white dwarf, which is the remnant of a star. And we know now that this is the electron degeneracy pressure balanced, which is balancing the gravitational pressure. On the other hand, if you have a massive star, anything less than 25 solar mass to 30 solar mass, it undergoes a supernova event where the star suddenly collapses and releases all its energy and ejects all of its outer envelope into the circumstellar matter. And at the very center, you have a neutron star, which is one. But if you have even more massive progenitor stars, then you end up with, in the supernova explosion, you end up with the stellar mass black holes. Okay, so just properties of a white dwarf. When I say white dwarf, they are roughly of the order of 1 solar mass. The maximum is 1.4 solar mass, thanks to the Chandrasekhar limit. And then they are 1,000 kilometers in radius. But the neutron stars, they are even more compact. They have a radius of 10 kilometers. So just as a fun fact, Sun is headed towards becoming a white dwarf. It will not undergo a supernova explosion. All right, so talking about what black hole binaries are. So these are systems where you have the compact object as a black hole, and they mostly come with a low mass companion star as their the donor. There are so what happens is the companion star, it accretes matter from the stellar wind itself. So what happens is, instead of forming an accretion disk, it directly starts accreting the matter. And because these are highly magnetized neutron stars, these have a magnetic field of the order of 10 power 12 Gauss. the matter then gets modulated by the magnetic field lines. So what you see here is sometimes presence of an accretion disk, but most of the cases you don't find an accretion disk in high mass X-ray binary, and then the matter gets modulated by the magnetic fields of the neutron star. On the other extreme, we have supermassive black holes. So these are black holes with 1 million solar mass or more. And this is an example of how this is a composite image. So this is Hercules A. It's one of the active galaxies. Or in cluster of galaxies.
So sorry.
No, it's
okay. Some problem with the internet that's going on.
Okay.
I hope that doesn't happen. Sorry about that.
So now I'll talk about what is the universality that is present in the accretion flows. Like I showed you what happens in a black hole binary system where you have an accretion disk and jets present in the system. But on the other hand, in quasar, you also have the similar process. You have an accretion disk and jets that are present. So in this case, what we see is the scale of the system for stellar mass black holes, which we also call microquasars. These are extremely energetic stellar mass black holes. These are of the order of light years. The jets are of the order of light years. And in this case, in case of quasars, these are of the order of millions of light years. So what we see is many of these accretion flows or this energy is related to accretion scale with some parameters. What we know now is these parameters are the mass of the black holes, the spin of the black holes, and what is the accretion rate onto these black holes. So there is a universality present in the accretion flows, and that's why it is very important for us to study both systems happening or accretion happening at small scales on stellar mass black holes or neutron star X-ray binaries or white dwarf X-ray binaries, and then scale them up and see how these these scaling laws behave for supermassive black holes and active galactic nuclei. This is a plot of, so like I said, these systems, the stellar mass black holes, supermassive black holes, they emit in radio. There are jets present in the system, and they are also bright in X-rays. So if you look at the relation between the radio luminosity and X-ray luminosity, you see certain universal features. One is there seems to be a correlation between the radio luminosity and the X-ray luminosity. These two are produced in completely different ways. X-ray are produced from the accretion disk itself, and the radios are produced from the jets. What this says is there is a relation between the radio and X-ray luminosity present for these systems, and they scale with the mass. So it scales from stellar mass black holes all the way to supermassive black holes. There's also a dependence on the spin of these systems and also the accretion rate of these black holes. All right. So now the key questions that govern in astrophysics, especially in high energy astrophysics, is how these accretion flows are around compact object and supermassive black holes. Are there universal scaling laws that relate to these two? And also how these impact the formation and evolution of large scale structures. So what we now know is the formation and evolution of galaxies. This is highly dependent on the feedback from the supermassive black holes. Vis-a-vis, the X-ray binary population is dependent on the galaxy host parameters like metallicity, star formation rate, stellar rays. So these are not two independent problems, but these are intertwined issues. So now talking about how the hot gas in early type galaxies look. So like I mentioned, the elliptical galaxies, they are considered as endpoint of galactic evolution. So in the Hubble scheme of galactic evolution, the galaxy starts from something like an amorphous irregular galaxy like a large Magellanic Cloud. It becomes a spiral galaxy with arms and dust, and then slowly, with the process of both like galaxy mergers with other galaxies, or with like the star formation slowly dying out, it turns into elliptical galaxies. So the elliptical galaxies are characterized by old stars and no active star formation rate. Many of these galaxies are also, they don't undergo any active astrophysical processes like mergers. So this is an example of this is an optical image of NGC 4636. This is the same galaxy that I showed in the first slide. So if you look at its optical image, it looks smooth and featureless, which means that it does not have any arms that you see, spiral arms that you see in Milky Way. You don't see any dust lanes in this optical image. However, if you look at its, so Chandra is an X-ray observatory with the highest spatial resolution. So if you focus somewhere close to its center, this is what you see. So you see a lower temperature at the center, surrounded by a slightly higher temperature surrounding this lower temperature. So Chandra has a higher spatial resolution but small field of view. If you image the same galaxy with XMM Newton, which has a slightly worse spatial resolution compared to Chandra, but a higher field of view, what you see is a larger picture of what is happening at the galaxy. You see all the processes which are related to also processes happening at the outskirts, which might be because of there's another galaxy present near this galaxy, and I'll talk about this in detail. So what you see here is there is a cold gas at the center, which also has anisotropes, but then surrounding this cold gas, there is a hot gas present there. So the temperature scale here, which, sorry, it's unfortunately not seen, the green is around 0.6 keV and the yellow is around 1 keV. And also this has an asymmetricity, this has a directionality.
Nazma, you said green is 0.6 kV.
K. And
So the green is cooler.
yes, green is cooler.
The center is cooler.
Yes. And
Fine.
this also you see a directionality to the hot gas temperature.
And this, sorry, the elliptical contour is like the
So
optical
yes, so-
galaxy.
Yes, so that is the D25. So this is where 95% of its optical light is contained. All right. So the temperature distribution of hot gas in elliptical galaxy, it contains a lot of information about what are the astrophysical processes that has impacted its formation and evolution. So for example, Asian feedback is a very important process that impacts the formation, the distribution of the gas. But then you also have another host of other processes. Like for example, if this galaxy had undergone merging event in the past, this hot gas also retains information of that. I'll show you about some examples of that. But then it also has information about the RAM pressure stripping. Like if this galaxy is moving through a dense intercluster medium, or it is interacting with another nearby galaxy, you will see that the effects of RAM pressure stripping or tidal tails.
Why do you see featureless in optical if it is merging? If it is merging, then there will be density enhancements which will trigger star formation.
This was in the past. If this galaxy had undergone mergers in the past, it will still have information on that. Yeah, and also there's other information related to if this galaxy, like, there are various dwarf galaxies which had this huge outburst of star formation. So you also see effects related to increased star formation in the past and its effect on the hot gas, specifically the metal distribution. So in this work, what we did is we did a systematic analysis of 70 elliptical galaxies with the objective of creating spatially resolved temperature plots, and iron maps. This product is released to the community, so anybody can go, they can download either the temperature map or also some of the meta products, which we created as part of the analysis. And this is this is a gallery of diffuse gas emission for a selected sample of galaxies. And what I want to show here is the difference in the behavior that you see amongst the temperature, the temperature and the iron abundance map for many of these galaxies. So for example, NGC 4636 is here. And what we see here is this cool front in the center, which is now we know it's related to the AGN outburst in the past. But then you also have galaxies which have another galaxy in its field of view. So this galaxy, the hot gas distribution, will still have imprints of this presence of another massive galaxy in its nearby. And there are other galaxies like NGC 4472, which has this presence of this tidal tail, which tells you that the motion of the gas is still present in this galaxy.
Sorry about my ignorance. What is the NGA atlas and CGA atlas?
Yes, so NGA is the Newton Galaxy Atlas. So this is the atlas created for the XMM Newton products. And this is the Chandra Galaxy Atlas. So for the same galaxy, we have both the larger field of view and the very highly high spatial resolution view. So what you can see is what is happening at the larger extent, like when you have galaxies present nearby, you can only see its effect with the XMM Newton observation, but not with the Chandra observation.
Do you know the stellar masses of the galaxy?
Yes.
So how much is that?
So we do have anywhere from roughly 10 power 11, 10 power 12 solar mass to very massive fossil galaxies like 10 power 16 solar mass. So there are some fossil galaxies also present.
16 solar masses.
10 power 15.
These are fields, all field galaxies. Is it confirmed that if they are all field galaxies?
No,
or
these are not field. Like you have, like for example,
groups also.
yeah, you have NGC 1404, which has this galaxy. We also have information, like we also created map for this galaxy. So when this was in the pointing view of
So it's a mixture of field and.
Yes, yes. These are all, there's a, and this is also
The
the,
selection, how did you do this? Is it like off from, okay.
so the selection is, we looked at the normal galaxy atlas, and we looked at the galaxy where currently no active, no bright AGN is present. We looked at how many observations were there in the past with XMM and Chandra. It has to be one with a better sensitivity. And yes, so these are the two main criteria that we
Yeah,
selected.
it's the question, the reason I'm asking this question is because like, I mean, what was in mind when we created, so when you guys, like when the group created this entire galaxy catalog and this, you know, the X-ray observations, I was just wondering that if there's a
Yes,
specific type of selection involved in this, if you want to look for this.
yes. So the first reason is the previous study for studying this distribution of hot gas have been either carried out with very certain kind of binning methods, or it has been only done in terms of the X-ray image itself. So for us to compare results like, radial profiles and temperature maps and iron maps, for us, we have to first go back and uniformly analyze it. Also analyze it with more than one binning method. Like for example, here, what I've shown. Yeah, the one that I've shown here is something which is called with a contour binning method. So in this, what we do is we bin the regions. So the way we select the spatial regions is if they have uniform surface brightness, you bin them at the same region. There are 4 methods that we have used this. One is called the annular binning, which has been done often, where we just take annulus around the center. Contour binning, and then we also take the weighted boronite tessellation. So weighted boronite tessellation is depending on if you have more photons here, you have a larger, so a lower area associated with it, and vice versa. So and then there's a hybrid binning, which is a mixture of both CV and ES. So the reason is, if we see uniform trends with all of the 4 methods, then we know that this is true. This is not related to the binning feature. This is more important for when I'll show the iron maps where previous studies have been as highly dependent on which binning method you see. The second thing is, Chandra and XMM have been operational for over 25 years, but nobody has done a systematic study. Like we now have, for many of these galaxies, we have more than one, sometimes even 6 or 7 observations. But how does this look in the global ensemble picture? Like, if you can create temperature maps and iron maps for all 70 of them, does it say something? So right now, what our group is doing, we are looking at many of these products. So we are looking at the global features and trying to see, like, one of the things I can quickly show and then I'll explain is, for example, this is a radial profile. So in this case, you see one peak, but then our group has also identified the presence of 2 peaks. If there's a double peak structure, if there's a structure where, it suddenly becomes flatter at the top, so does this mean a certain type of galaxy? Does this mean that they have certain processes? So that was one reason why we went and redid the.
This is, I mean, you have estimated the temperature, but basically, it is the peaks of the intensity of the X-ray, whatever band you have chosen.
Yes. So this is, if you take, this is a two-dimensional temperature map, but if you just take a one-dimensional radial profile along this,
One cut, yeah.
yes, one cut, then you see this.
But isn't the temperature map also?
So it's basically converted.
I think it depends on the hardness.
But what is the green one?
I'll talk about this later, yeah, when I come on this, but if you want, I can just actually quickly mention. So in this way, what we have done is we have used 2 different binning methods. So in one binning method, what we did is we fixed all the abundances and then we fitted the temperature. But in the second one, we kept the abundance of iron free. And then we looked at if there is any difference in the temperature measurements. The thing is, with XMM, there is a problem of, like, if you go on the outskirts with lower sensitivity, like, if you have lower statistics, it sometimes gives off false, like, the temperature measurements become erroneous, and that has to do with the CCD itself. So in this case, what we were trying to see is at the absolute outskirt, can we trust the temperature measurements? But what it says is near the center, the predictions are more or less similar. If you keep the iron free versus the iron abundance free versus iron abundance as fixed, they more or less give the same similar trend.
That's why it's disturbance. So I can read, if I read the RKPC, so that it says 110 and 100. So where is the center of the galaxy?
The center is here. So we start from here.
I see. And
then you are going this way.
And
So
how,
That is in box.
that is
I understand, but I was thinking that so you're going from the slope.
The higher energy is speaking at outer part.
yes. This is exactly what it's saying. And I'll talk about this in detail, but this is what it's saying, that this is not an artifact. This is actually what you see in the radial velocity measurement as well.
I mean, you also saw on the images that there is the peak is shifted
Yeah.
from the.
Yes,
Yeah, but the all of the radial this radial profile is what goes into the input for all the galactic and cosmological simulations.
No, no,
So,
sure.
so for this,
More
yeah.
quantitative way.
Yeah.
Yeah, no, I was just, whenever I saw the central pole star, I was thinking of cooling films. But it's, yeah.
All right, so in this case, like you see in for NGC 1404, which has another galaxy in the field of view. Now, if you look at its if you look at its detailed temperature and iron abundances, what we see is the distribution of the gases influenced by the other galaxy present near the elliptical galaxy. But what I would like to explain further is the case of NGC 4636. So NGC 46, the hot gas in NGC 4636 has become like a poster child for hot gas distribution in elliptical galaxy. So in this case, what we see with the temperature map of XMM is, we see a colder gas at the center of around 0.6 kV and a hotter gas which has a directionality surrounding this cold gas. And this is also what we see with the one-dimensional radial profile. So the advantage of one-dimensional radial profile is like for two-dimensional maps, sometimes we are limited by statistics. So some of the features that we might see might not be even statistically relevant. But if you see in the one-dimensional radial profiles that a temperature peak is actually happening after 10 kiloparsec from the center, then you know that the hot gas, the asymmetric distribution is shifted from the center and situated there. But if you look at the iron maps, they tell you a different picture. So again, I'm sorry about the label here, but just quickly going back to this one. So in this case, this is also there. Okay, so green is 0.2 solar metallicity, and yellow is up to 2 solar metallicity, so twice the solar metallicity. So in this case, what we see here is at the center, you see a subsolar iron abundance. But along the outside the center, at the outside the center, you see a higher solar abundance of iron. This is also what we see with the one-dimensional temperature, abundance map, where the peak of the iron abundance actually happens away from the center. Now the question is, in elliptical galaxies or in galaxies, you always see more stars present at the center, and the chemical, the way the metals are produced are either from supernova explosion or from stellar wind of the massive stars. So now the question is, in this galaxy and also in several galaxies, we see the core is depleted of metals. Conversely, we see a metal distribution which seem to be anti-aligned with, or rather aligned with the what we think was the jet present in the when the AGN was active. And what we think is this transportation of metals also was fueled by the jets present in the system. So the metal distribution is also related to the AGN feedback. Now, creation of iron maps or studying chemical evolution in galaxy is highly limited by how sensitive your instrument is or how sensitive your measurements are. So with XMM, we could only do it. We could only do a statistical analysis or a significant statistical analysis for a very few sample of elliptical galaxies. It's just XMM is not sensitive enough to study chemical evolution. So I'll talk about the future mission in which this issue of chemical evolution in galaxies and in cluster of galaxies will be targeted. Yes.
If I look at that 2D image, it's in the reverse direction, the hot gas and the metal level.
Yes, that is correct. And we don't understand why. We just know that it's not at the center. We also don't know that how sensitive, like the direction.
From the outside.
No. It's on the other side.
It's on the other. Yeah, the direction is on the.
In radial profile, you will see that.
Yeah.
I also
Maybe
noticed.
that's not make a difference.
In radial profile.
Yeah.
But then, could it be that you have an old center that could also be a signature of agency, right?
This
Your-
one.
No, the center is full.
Oh, yeah, that is from, that's definitely.
Your gas is being
Yeah.
just pushed out.
Yes,
and
yes,
That sort of decreases because it's a center of the gravitational potential.
that's true.
Yet that's what the
Why do you
gas.
have twice the solar metallicity at that region?
No, how reliably can you trust it's two solar metallicity?
Yeah.
That's the bigger question. We know it's depleted. We know that definitely the center is depleted from from especially the iron element. But
But also this is an elliptical galaxy, so you expect metal rich.
no, actually metal rich.
No, sir, I
This
was
is
going
gas.
to ask, how are you getting the metal? It's from iron line or from optical?
No, this is from Ireland. So the way we do is we so all of these are done with the collisional ionization plasma model. And so with that, if you now the problem is you can for iron lines there is iron L lines which happen around less than 1 kV, around 0.5 to 0.8 kV. And this is a blend of lines. In that particular area, you expect oxygen lines, you expect neon lines. So it's very difficult to disentangle which line is which, especially with an instrument like XMM. This is MOS, not even RGS. This is MOS. So our estimate on this chemical abundances is also highly limited by how sensitive your instrument is. So in this case, what we did is we also tried fitting the iron H-like and He-like, which happens at 6.4 to 6.9 kV. But in that region, your XMM effective area also goes down rapidly. So all of these are rather, I would say, precursors to what your next mission should be.
But how do you get the spatial profile of metallicity?
Yes, so we do the same. Like if you look at the region files here, so these are the same region files where one we fit with a fixed abundance, and the second one we only vary the iron abundance, and we again fit the same spectrum. Yes.
So why do you not studying the spiral galaxies for the same phenomenon?
That's a very good question, because the hot gas there is very hot. So it's very difficult to disentangle that if this particular contribution to hot gas is because of star formation happening, or there is an AGN which impacted so it's a more turbulent system. But from the technical side, the issue comes from the background modeling. So in this case, we know the background for XMM, we just use the blank sky files and you can tailor it. But in that case, when you know your background itself is varying rapidly because of either it's related to the intrinsic hot gas or related to the effects of the star formation rate or something. So your background is very difficult to model. So this analysis for now, we could only do with elliptic analysis. I think you had a question.
No.
All right. All right, so now coming to the energetic universe, and I'll show again the plot of the radioluminosity versus the X-ray luminosity for the whole sample of stellar mass black holes and supermassive black holes. And this particular plot, or this particular area where this correlation lie, are called the fundamental plane of black hole activity. And if you zoom in on the stellar mass black hole area, what it looks like, it looks like there's one single power law which extends from lower luminosity to higher luminosity for supermassive black holes. But if you look closely here, it actually is not a single power law. In fact, this is a plot of the radioluminosity and the X-ray luminosity of all of the outbursting black holes that had gone into outburst, and we have radio and X-ray luminosity measured for these sources. So immediately you can see two tracks present here. So one track is called the standard track, in which the radioluminosity is related to the X-ray luminosity to a factor of 0.6. And what we call these are radiatively inefficient in accretion. On the other hand, there is an outlier track where the index is steeper, of the order of 1.4, and we call them as radiatively efficient in outflows. Now, if you look closely in this two plot, you will see two sources dominating these two correlation. So the green ones is GX339-4. This is a stellar mass black hole X-ray binary system which has gone into multiple outbursts in past 20 years of observations. And the other one is X1740. And this is a prototype of the standard track.
Very much like VRS.
Yes.
Only lower energy.
Lower energies. And this is the other prototype of the outlier track, it's H1743-322. So what we did is we looked at these correlation more closely. So this is an RXT-ASM light curve of JX339-4 and H1743 over its 16 years of its history. And you see that this source has undergone multiple outbursts. And whenever it went into outburst, there have been simultaneous X-ray and radio measurements carried out for both of these sources. So what we did is we looked at the correlation when the source was undergoing a peak into outburst, and then when it was declining from the outburst. So we divided this sample depending on when if the observation was carried out when the source was still rising in outburst, and this when the outburst had happened and the source was declining from the peak of its outburst. And this is marked by green and blue, red and blue arrows here. And all the X-ray observations were carried out with RX-3 and all the radio observations were carried out with either ATCA or VLA. And if you look at the hysteresis diagram of a black hole binary, so what happens for a black hole binary, if you look at GX339-4, it is in the quiescent state, and then suddenly something triggers, and then it starts rising in its intensity. So if you look at its spectral hardness and extra luminosity plot, say A is the point when the source is in the quiescence, and then instability set in, and then the source starts going into outburst. So it starts rising in its luminosity. At a certain point in B, when it is in the hard state, what we call the spectrally hard state, jets are present. Jets are actually quenched or not present in the soft state. So at a certain point in B, it makes a switch to the soft state where it goes from a hard state where the spectrum is hard to a soft state where the spectrum is soft because it is inherently dominated by the accretion disk itself. And in this particular state, what we see, the jets are not present anymore in the system. Conversely, when the outburst ends, when the source starts going back to its quiescence, it undergoes a decline in luminosity, and this spectral transition from soft state to hard state happens at a different luminosity. It goes into the hard to soft state at a higher luminosity and comes back to the hard state at a lower luminosity. This is very similar to what we see in magnets. Magnets retain information of its state, and this is what we call as hysteresis. So in this case, what we call this as the hysteresis diagram for a black hole binary. So what we looked at is the behavior of the jet. So these are the points for both GX339-4 and X1743 when it was in the rising hard state and in the declining from the outburst peak. And both of them we see that it behaves like a standard track source. It has an index of 0.6. Conversely, we see that the behavior when the source is going to the hard state is different. So the behavior of the hard state from the rising hard state to the declining hard state shows a different behavior, which means that it is similar to a jet hysteresis present in the system. But if you look at a global picture, what happens if you, so GX339-4 and X1743, these are two sources which are black hole binaries with a low mass star as a companion. Now, the other two systems which have a massive star as the companion are Cygnus X1 and Cygnus X3. These are black hole binaries with massive star. But if you look at its radio and X-ray luminosity, you see difference in the behavior in these two types of systems. So the green ones are all the source GX339-4, and the blue ones are X1743. So X1743, it undergoes a steep decline, and that at very low luminosity, it sort of flattens and approaches the standard track. Cygnus X3 is one of the brightest radio loud X-ray source that we have in our galaxy. And in this case, what we see is a very amorphous relation. There's no strong correlation that you see in the radio and X-rays. The reason is for Cygnus X3, the system is has an orbital period of hours. So what we think happens for Cygnus X3 is the jets get enhanced by the stellar winds in the system. Conversely, if you look at Cygnus X1, which is again a black hole binary, but with days as the orbital period, in this case, what we see is the radio emission is getting absorbed in the stellar winds. So this gives you a global picture of what happens when you have to consider stellar wind interaction with the jets present in the system. But the question, yes, sir.
But, I mean, is it a good idea to compare both these? Because Cygnus X1 is a persistent source, while GX is an
Transient.
transient, right? So, I mean, why is it a good comparison to make? I'm not getting that.
It's not a good comparison to make, but it's a comparison to make if you how the jet interacts with also the stellar wind in the system. Like for the same behavior of jets and stellar winds, for Cygnus X3, we see a radio loud behavior, whereas for Cygnus X1, it's a radio quiet behavior. This is to compare how all of this look. And yes, you mentioned, is it a good thing? So what we did is, we also looked at how its bolometric luminosity is related as a function of its L Eddington. So we are sort of normalizing it with the stellar mass of the black hole in this case. What I'm trying to put a global picture, like compared to what we have for this, is in this case, it's only the mass and spin and the accretion rate. But is that enough? We do see many of the sources with high stellar wind or high winds present around it. We see a behavior which is different from the standard correlation or the fundamental plane of black hole activity. So looking at Cygnus X1 and X3, it gives us an idea that how important are winds or stellar winds in the system. But the problem becomes even more complicated if you put radio X-ray binaries in the system. So this is the standard correlation of 0.6 of all the black hole binaries. And this is where all your neutron star X-ray binaries, which have a jet present in the system, lie. So neutron star X-ray binaries show a even more radio quiet behavior compared to black holes. And now we don't understand why. Is it because they have surface? Is it because they have high magnetic fields? Or is it because the accretion, like the launching mechanism of jets needs to be modified for neutron star binaries compared to X-ray binaries? So in this case,
observation, the mechanism is a proposal, theoretical proposal.
Yes.
That might change, that might get completely opposite, polar opposite. Okay, so this, so how many neutron star sources have been put there?
In this?
Yeah.
Yeah, so this is about 15 or so.
Oh, so this plot has neutron stars.
Yes, these are
These are the
neutron
ones,
stars.
those ones.
Yes, the lower ones are all neutron stars.
How are they radio?
So these are observed with VLA and alpha. So there are some neutron star binaries with in low mass X-ray binaries which have jets present. But then the problem is, if you see neutron star binaries with a high mass companion, are there jets present? So there have been indications now for 3 sources with some radio emission present for neutron star sources with high mass binaries.
And those are the.
Those are actually not put in this plot. The high mass X-ray binaries are not put in. These are only for low mass X-ray binaries. And the problem is, with higher magnetic fields, are the jets getting weaker? Is the are the magnetic fields an indication of the strength? Yes.
Should be. A very strong magnetic field, and overall it's a dipolar field. It will not allow, jets.
Yes.
Go very long.
Yes.
By weak you mean it's very small scale jet.
No, actually,
Very powerful jet.
Not very powerful.
not very.
Doesn't
So
launch it.
radio, yeah.
Cannot help.
That is different. You have to open field lines, but it is very strong.
So it's,
We dipolar,
it's
no?
just bending it. You're
Yeah.
saying trapping the
Yeah.
jet by the magnetic field.
Yeah, but the current simulations do not account for this at all. Like right now, we don't know how to
What
put.
simulation center?
I was going to say.
Like for observers, we are like, okay, we go searching for simulation, we don't find any. But yes, so the question is it because of high magnetic fields or is it because it has surface? Is it the launching mechanism is different? The answer, we don't know. In fact, for neutron star X-ray binaries, including the, like this picture shows that there's a certain clustering feature present in the radio X-ray behavior for stellar mass black holes and radio X-ray behavior for neutron star X-ray binaries. All right, so now the bigger question is, how do you distinguish neutron star and black holes in X-ray binaries? The question is more complicated than it looks. For neutron star X-ray binaries, you need to detect the presence of a surface. So for example, if you see pulsation present in the source, either in radio or in X-ray or in gamma ray, you know that this has to come from a surface and you can say for sure that this is a neutron star. But for several of the sources, in fact, there are very few of a very small fraction of known X-ray sources where pulsations have been confirmed or detected. The other indication is if there is the presence of a surface, like if you have cyclotron scattering resonance features. So if you, these are magnetized objects, so the magnetic field gets split into Landau levels. And then if you have an electron moving in it, so when it makes this transition between the Landau levels, you get an absorption in the spectrum, or if it's a optically thin plasma of, say, for wide dwarf, you see them in emission. So this is one sure shot method of saying that this compact object has a surface and a high magnetic field. The other is the thermonuclear burst. So you know in many of the X-ray binaries, when you have matter getting accreted onto the surface of the neutron star, suddenly they like all ignite in a flash in the thermonuclear burst. And often you see this very peculiar called photospheric radius expansion, where you know that this only happens if this is a neutron star, but not a black hole. For black hole binaries, to confirm this is a black hole binary, it is even more difficult. For that, you need to measure the radial velocity of the companion star. And then you know what the mass of the companion star is, and vis-a-vis you can estimate what is the mass of the compact object. And it is, if it is more than 4 solar mass, you can be sure that this is a black hole, because no equation of state for neutron star predicts a mass of a neutron star more than 4 solar mass. So this is how Cygnus X1 actually was confirmed as a black hole. It was by its radial velocity measurement. So both of these methods are very time intensive. It is not meant for quick identification in era of like, larger surveys and detection of many unknown X-ray sources. So what we did is we tried to explore if color intensity diagrams could be a means of distinguishing this black hole binaries. So in this case, if you look at, so let me first explain what the axes are. So on your one axis is the soft color, which is the information of all the photons below 6 keV. Your other axis is the hard color, which is the information of the photons above 6 keV. And your third axis is the total intensity of these sources. So in this case, what we do is we look at how these sources or this source, do these sources have a clustering property in this three-dimensional color intensity diagram. And we do see that. We do see that for black hole sources and neutron star sources, there is a clustering property that exists in this color intensity diagram. We investigate a bit further. Can we use this clustering properties to reliably predict the type of an unknown source? So what we did is we looked at 3 machine learning methods to just give a small overview or a brief overview of what they are. What we are looking at is the clustering property. So we look at clustering methods for machine learning. So one is called the K nearest neighbor, in which if you have the black holes occupying here and neutron star occupying here, and then if you have a source here, which is your unknown source, so depending on if it is how its neighbors are, like if its neighbors are 60% of black holes, we call it this source is 60% probable of a black hole type. If its neighbor are 40%, then you put a probability on depending on what its nearest neighbor are. Okay. In the support vector machines, what you do is, so these are black holes, these are neutron star, and if you can define one linear plane which separates these two population out, and then if you have your source here, your unknown source here, depending on what your distance of the source is from the linear plane, you can define what the probability of this unknown source is. So this is for a linear vector machine. You can also do it for a non-linear vector machine in which the vector support machine, where you can use a non-linear plane to demarcate between these two populations. So these are clustering mechanism. What we also use is something called the Bayesian Gaussian process, in which what we do is we use two kernels. We use either a Gaussian kernel, which is given by this, or a Laplacian kernel. And in this way, in this case, what we do is we look at all the distribution of the sources along with its error. This is not possible in the first two methods of clustering. You don't account for errors there. In this, you also account for errors. And depending on how your unknown source looks, you can define a median probability of the unknown source belonging to either of the two class. So this is what we get. So what we do here is, I'm sorry about the labels, but what we are showing here is, in this case, what we do is we know this source is a neutron star. Let's see if our machine learning can predict the correct type. So what we have is the true label versus predicted label. So if you have a pulsar as a true label, it always gives you pulsar as a predicted label. Okay, so it is very efficient in distinguishing between pulsars, especially accreting pulsars. The problem happens is when you have black holes, especially black holes in quiescence. So if you have black holes and neutron star in quiescence, they sort of seem to mimic each other's behavior. And that's why the machine learning methods here are not very conclusive. And this is what we're currently working on, how to tune this method further to distinguish quiescent neutron star and black holes better. All right, and the reason why we need to look for these sources is because this is a cumulative distribution plot of the black hole masses. So over here, the green ones are the black hole masses from X-ray binary population. These are the black hole masses which have been detected and confirmed using in Milky Way using the radial velocity measurement. These are all radial velocity measurements. The yellow ones are the done. So this is including O2. So what we see is black hole, we tend to detect massive black holes compared to what we see in X-ray binaries. So now the question is, are we missing out on seeing massive black holes in X-ray binaries? So we have to go and hunt for them. Or the question is, because these black holes, which are detected from LIGO observations, these are black holes which were created at cosmological timescale. And over the times, they have finally undergone their stellar evolution and have merged. So is there a different synthesis method which were leading to higher masses of black holes in the past? If this is true, then is that why we are inherently detecting more massive black holes? So the question is twofold. With O3, we would know if this two distributions still exist, or are we detecting more lower mass black holes? And also for looking, we need to go search for more massive black holes in X-ray binaries. It is, the run is concluded, but I don't think any results are out yet. Like we still don't know how many detections they have. Like we do know what are the detections, but like, later they tell you all the like all the statistics of the distribution, how many merging black holes they have detected, how many they think that it could be a neutron star. So those numbers are not out yet. So this would change with O3, but how much would they reconcile with what we see with the X-ray binary population is something that
we have another alumnus from my batch, who is actually working on this black hole mass function, basically working from the other side.
Okay, that's interesting.
And the reason, I don't know.
No, I don't think any of the O3 data, the run just finished, so I don't think if any of the data is still out for public. But they are releasing all the triggers for public, but these studies are not out yet. Sorry? Yes. All right, so in summary, feedback from AGNs, very important for studying the formation and evolution history of galaxies and cluster of galaxies. There is a universality present in accretion flows, which is related to mass, spin, and accretion rate, and also the type of compact object. And color intensity diagram, promising avenue for identifying this neutron star and black hole binaries. And the more important thing is, for the next generation of telescopes, how the feedback influences chemical evolution in galaxy. The answer lies in the next generation of telescope. One of them is already currently operational. It's called PRISM. It's a microcalorimeter, which is currently operational. And the next generation is Athena, and also a probe concept called line emission mapper, which I'm a member of. And this is a mission which is put forward by people at Center for Astrophysics and at Goddard, with a huge membership in around the world. And one of the main objective of this is studying the chemical distribution, not only of iron, but also of oxygen. And that would be completely game changer. This is going to be operational in 0.2 to 2 keV. So even lower energies compared to PRISM. PRISM currently, the gate valve is not open, so we are only restricted till 1.7 keV. All right.
Links is also.
Links is over.
Links is also.
Links is not approved any. So yeah. Links was supposed to be, it was not as sensitive as line emission mappers, but it had larger collecting areas and mirrors. So that has not been approved. All right, so I'm very excited to talk briefly about ExpoSat. So this, as Professor Aditya had mentioned, this was launched on 1st January this year. And it has two devices, two payloads. One is the X-ray spectroscopy and timing payload, and it is an array of swept charge devices. Swept charge devices, they don't have any positional accuracy, but because it will always be looking at whatever the main instrument Polix is looking, so you will get an information of how the timing and spectroscopy behavior of the source is. And this is operational in 0.8 to 15 keV. But the main instrument is Polix, or polarimeter instrument in X-rays. This is a hard X-ray, or rather we call it medium X-ray polarimeter. So IXP, the other polarimeter instrument, this is operational in 2 to 8 keV. For Polix is operational in 5 to 30 keV. So this is even harder than what IXP is. And this consists of a lithium beryllium scatterer here, and it is surrounded on the 4 side by proportional counters. So if we expect the polarized light to come from here and get scattered from, so this is a Thomson polarimeter, and it gets scattered here, and depending on what your directionality is, it will register intensity on the 4 proportional counters, and you can get back the information of your incoming photons from this intensity distribution on the proportional counters. Okay, so thank you very much, and I'm happy to take any questions.
Okay, questions? Unique?
Yes. So that was a very interesting talk.
Thank you.
So my question is, when you're talking about the detecting whether these things are black hole binaries or not, can you exactly localize their positions?
Yes, so all of these sources that are detected, so